Today we're going to start talking about IA32 instructions, so I'm pretty excited about that. We introduced the sort of the data, or where variables can be stored, and it's kind of funny because you take CS1 and Mike talks about this is how to create a variable, and whatever variables you need you can create and name them whatever you want and blah blah blah. But when you're at this level, you have a fixed set of variables and there are what they are, and you have to use them the way that they need to be used. So we're very limited. We're at a very low level of the system. But we talked about these registers, and remember that when we have these nested boxes, what we're saying is that EAX is a 32-bit value. You can refer to the low 16 bits with the name AX. And of that 16 bits, the top 8 bits can be called AH, and the bottom 8 bits can be called AL. So just be aware of all of that. We also had EIP and E flags, which EIP is the program counter. We call it PC. Many processors call it PC. For whatever reason, Intel decided to call it the instruction pointer. So just be aware of that. Now, the instructions follow this pattern. You have some opcode, just like the assembly code that we looked at before. And then you have operands, 0 or more operands, depending on what the instruction is. There certainly are 0 operand instructions. And these are some examples. You hopefully will understand all of these by the end of today's class. The important detail here, though, is that we follow a different syntax than WCS5X. And I actually prefer this. I took 5X when I was an undergrad and loved the classes. So, in fact, I was a 5X TA and all of that stuff. But this syntax is slightly different. We call it the AT&T syntax. And it's the syntax that is used by the GNU assembler by default. I believe there's a way to switch it into Intel syntax, and if you have TAs that are also double E's, which there are a few, then they probably will help you figure it out, because they may prefer to grade Intel syntax. But I prefer AT&T syntax, so that's what we'll use in the lectures and the assignments and so forth, at least in the write-up, so just be aware of that. Now, the issue with this, the difference between the two, is that the Intel syntax and the AT&T syntax flip the order of the operands. And I find that this is almost universally better than the Intel syntax. I've always been frustrated that the destination is the first thing. I don't know why. That sort of morally offends me, or it offends my aesthetic sense. And so AT&T syntax is a little bit nicer. Everything moves left to right, except for comparing and subtracting. Those ones get messed entirely up by this AT&T syntax. So just be aware of that. But that's why we follow this funky syntax. And if you've already taken 5X and you're familiar with IA32 assembly, this may give you some headaches as you try to sort it all out in your head. We have various categories of instructions: data movement, arithmetic and logical instructions, flow control, our conditional and unconditional jumps, and then many other things that we are going to skip on. But this will be enough, hopefully, for the bulk of the programming that you'll do in IA32 and CS24. If there's ever a situation where you need additional instructions, I generally will tell you what they are and how to use them, and I give you copies of the IA32 manuals. They'll be put up online when the next assignment comes out, and you can look up pretty much any instruction you want. Volume 2 contains all the instruction descriptions. It's divided into 2 parts because there's so many. CISC, what can I say? So data movement, move with sign extension, move with 0 extension, push and pop. These are the data movement instructions that we generally care about. There's more, but these are the ones that you'll get most of the bang for. Typically, we prefer to put suffixes on our instructions so that we can sort of explicitly state what is the size of the data that we're working with. And these are the meanings of the various suffixes, so B, W, L, and Q. So L is the weird one out. L is for double word, and then Q is for quad word. And so you'll have things like this: move L, ECX, EDX. Now, do you need to say that I'm moving a double word in this situation? The assembler can infer it from the arguments because, hey, they're both double words, so you're probably doing move L. It's just sort of one of those coding style things where it's nicer when you can state the suffixes and then it's really easy to read. So just be aware of that. push VAL. Again, do we really need to say we're pushing a byte? Not really, because it's obvious from the fact that I'm pushing AL. And in fact, if you were to not have it match, then you'd probably get an error from the assembler. But this is just the way that you can write in AT&T syntax. Okay, moving with sign and zero extension. Think about it. I'm moving from a narrower value to a wider value, and I have to decide what to do with all these unspecified bits when I move from the narrower value to the wider value. Do I want to just put 0 bits in? That would be moved with 0 extension. Or am I moving a negative value, or a potentially, I should say a sign value is really the right thing to say, and I want to extend that sign bit all the way through. So you have move SBL. I'm moving with sign extension a byte into a double word. The L actually stands for long word. That's why it's L. But anyway, so byte AL into double word EDX, and we're going to extend the sign bit all the way through EDX. And then move ZWQ, so I'm moving a double word into a, or no, I'm not, sorry. Yeah, a word, so 2-byte value into a quad word register, which again, this is probably one of the few places you'll actually see one of the R registers, and it will do 0 extension. So any of the unspecified higher order bits will be 0. Okay? So any questions? Oh, yes?
Can you make a constant different size?
Can you make a constant a different size? Well, so it's interesting because when you specify constants, which we haven't really talked about, since we have a CISC architecture, the instruction will encode that constant in basically as few bits as it needs, and just based on the target, it will go ahead and expand that on the processor when it executes the instruction. So in a sense, we don't really care what our constants sizes are. The instruction will encode it. Yes, sorry? Yeah, extending the sign bit. If you remember, like if you had an 8-bit value and it's a signed integer, then using 2's complement, if the top bit is 1, that means it's a negative number. And you can refer to the first lecture to see how that actually is represented. I'm not going to go back and repeat all that just for the sake of time. But the top bit will be 1. And so if you are going to move that into a larger register, yeah, like I have your AL into EDX, if you didn't make sure to update the sign bit properly, then you would end up having a positive value. So you have minus 12, and you move it into a 4-byte register, and now it's not going to be minus 12 anymore. It's going to be some positive number. And so it turns out that when you do sign extension, you need to set all of the upper level bits to be 1. And I can't remember all the details as to exactly why, but if you go and look at the math, it'll make perfect sense. But the resulting number should also be negative, and so that's why we set all the upper level bits to 1. Okay? Any other questions? I know that doesn't go into all the detail, but we just don't have time. And I didn't prepare an answer anyway. Okay, operand types. We can have immediate values. The way that we specify immediate values, you have to put a $sign on the front of it. Because if you don't, the assembler will assume that it's an address, a memory address, and they will look up a value at that memory location. So you have to put a $sign on the front. Registers we put % in front of, which again is slightly annoying, but you just get in the habit of doing it. The AT&T syntax is very, very verbose, much more verbose than it strictly needs to be, but hey, whatever. Okay, so this is an example of moving 42 into EBX. So like it says here, you have a value 42, and the fact that it takes up 1 byte is not really relevant to us because the assembler will encode this instruction in as few bytes as it can, and then it will move that into the register EBX, and so you'll get 00042. So if you were to look at BH, it would be 0, and BX would be 42, and so forth. Okay, questions? All right, so that's how this works. Memory referencing is really rich in IA32. It's super nice. You can do so many different things. Part of the reason why it's so complex is because it makes it very easy to manage arrays or structs or arrays of structs. It just becomes very straightforward to do all of this stuff with the memory support, the memory access support that IA32 has. So absolute memory access, just put a number without a $sign in the front, and it will treat it as an address. And you'll load that value into a particular register, or you can write from a register into a value. I'm just having these as examples. Indirect memory access, so I want to take an address from a register. I just put that register's name in parentheses, and now it will go ahead and use the value in that register as an address to do a lookup. So it says here, move W%CX, so I'm moving a 2-byte word into the memory location specified by the address in EBX. Okay? And you can see that you have to be a little bit careful because EBX is definitely not just a word. It's a double word because we're doing 32-bit and we need 32-bit pointers. We need 32-bit addresses. So that's why the address is specified in all of EBX, not just BX or something like that. Base plus displacement. So if I want to have accesses that are starting at some base address, but then the register says the offset from that base address, then I can do it like this. So there's an immediate value or a literal. Those are basically synonyms, immediate values and literals. So move L -8% EBP into EAX. Okay, so we're basically saying, which is kind of interesting because you can think of it in two different ways. You can either say, I have the starting address is variable, and I always have a fixed offset off of it, which is in fact how we will be using it a lot. Or you can say I have a fixed start and a variable offset. It's just which way do I want to think about it conceptually? Okay. Let's see, index memory access. So now you can have two registers. So one register holds the start of an array, and the second register holds the offset from the start of the array. So it'll just add those two registers' values together and then access the value. You'll notice that the two registers have to be in parentheses. You can add a constant in there. You can see that the math gets even more sophisticated. So a base register plus an index register plus an offset. Well, this is really nice if you have arrays of structs. Okay, and like I say, these array elements are bytes so far, so we're referencing individual bytes. So yes, here's a few examples just to quiz you, see if you get it. So EAX is 150, EBX is 400. So what memory address are we accessing here? Really easy, right? Yeah, 550. We just add the two together. So -200, EBX, EAX, well, that wasn't very creative. So you see, this time it's 400 plus 150 minus 200. So if it was 550 before, then now it's 350. Okay? Pretty straightforward. Any questions? All right, even though we have a lot of stuff to cover, I want to make sure you guys, because this is going to be so important as we get into all of this stuff. Now, last thing. We said we can have arrays of bytes, but if I have an array of bytes, that's not very useful. Most of the time, we don't actually use arrays of bytes unless we're processing string data or something like that. So it doesn't really help me if I want to have an array of ints or an array of structs. So we also have scaled indexed memory access, where the scale factor basically is akin to the element size of the array that we're accessing. And we have this lovely syntax. Open parenthesis, comma, reg s. So basically what we're saying is the first value is not specified, but the second register value is, and a scale is specified. And it will just multiply that register by s. Now notice our s's are all powers of 2. So really all we're doing is just shifting this register. So that's why we can do multiplication and it's fast. Doesn't affect our memory addressing very much. We can add in an immediate value. We can add in a base register and an index register. Notice that the index register is the one that is multiplied. So this is why you can think of it as array accessing, where the elements are a particular size. So if I want to have an array of ints, and ints are 4 bytes, then I can just use the reg b as the start of my array. Reg I can be the element number, and then s can be 4. And that way, as I increment my element number, as I traverse my array, the memory access will just do the right thing. It'll just move forward 4 bytes each time the index increases. And then we can also add in an immediate value as well, if we would prefer to. Okay? That make sense? Let's see, yeah, so arrays with elements that are 1, 2, 4, or 8 bytes. EX is 150, EBX is 400. So what address this time? 600, right? So it's just 150 times 4. I know you guys had the answer way faster than you started saying it. But anyway, so yeah, 150 times 4. Okay, here's another one. 350 EBX EAX2. Remember, it's the index register that is multiplied by the scale. So we have EAX is 150, times 2 is 300, and then we add in 400, so that's 700, and then we add 350 to that. So we end up with 1050. Okay? Did everybody get the same answer? Pretty much, if you tried? Okay, so we have M1050 here. All right, so this just illustrates how these things work. And they are used so much. This is a chart that was in the IA32 manual. You can probably find it in the part that talks about instruction and data access and so forth. Very, very helpful. The base register can be any register, any of the general purpose registers, I should say. The index can be anything but ESP. You're not allowed to use ESP. You're allowed to use the same register twice if you prefer. So EAX, EAX, 4 would be fine. Why would you do that? Well, you'll see a reason why you might do that in the second assignment. It's kind of a fun little trick. You can use this memory calculation stuff to do basic arithmetic pretty easily. If you want to take a number and multiply it by 5, for example, you can do that. Okay, so we have a scale and then a displacement. Now, there are constraints about what you are allowed to use as operands, types of operands. So the source argument can be an immediate value or a literal that you put in. Remember, you put the $ in front of it. Then you have a register, and it can be memory. The destination has to be something that's writable. The destination cannot be an immediate value, or else that wouldn't make any sense. Also, both of these arguments are not allowed to be a memory access, by and large. Okay? So if you want to move something from one location to another location, you have to move it into a register using your memory addressing, and then you have to move it from the register into something else, okay, into another memory location. So that's kind of an important constraint if you need to actually move data around in memory. Okay, so these apply to basically all the instructions. You want to add two numbers that are in some memory locations. You've got to move one into a register. Then you could add the other memory location into that register, and then you could move that register's value somewhere else. So it's pretty straightforward. Arithmetic. So we'll start going through all of these things. We have our unary arithmetic operation. So I want to increment or decrement. So when you do like I++, probably the process or the compiler is going to issue instructions like this. Negate, I want to do 2's complement negation. I want to turn 42 into minus 42. Or I want to do 1's complement bit inversion. Then that would be not. You have a not instruction as well. You have these operations. Notice dest becomes dest plus source, or dest becomes dest minus source, and so forth. This is why I don't like sub in the AT&T syntax, because it's a little bit confusing. You're taking dest and you're subtracting source from it, but I suppose it's fine enough. Anyway, the rest of them I feel like are all very self-explanatory. And yeah, you can specify the byte width. Again, the assembler can infer it, so it's not strictly required, but it's just a nice thing to do to your the people who read your code. Okay. Here's an example of a memory access. So we want to take EBP plus 4, get the value at that memory location, and add it to EAX. So EAX will accumulate the result. Okay? Let's see, shift operation. So we can shift right, shift left. Notice we have arithmetic shift left and right, and we have logical shift left and shift right. Of course, shift left is, there's no difference between logical and arithmetic shift left, so we go ahead and just, they're synonyms for each other. They'll actually emit the same opcode. And K here will be either a constant or it can be the CL register. And so if you want to shift something left by 4 bits, you can write it as shoal 4, comma, and then whatever register it is you want to shift left. Or if you need to shift by a variable number of bits, because you're not sure, you need to compute how much to shift by, you can set that in the CL register, but that value has to be between 0 and 31. Can it be 32? I can't remember if it can be 32. The slide says it can, so maybe that's right. Okay. You'll have to check the documentation in the IA32 manual to see if you can actually specify 32. Okay. So you also have rotate operations, which are interesting. You can use them sometimes for curious tricks, but you have rotate left, rotate right, rotate through the carry flag as well. So this is kind of nice when you want to do things based on the value of bits. You rotate into the carry flag, and then you do a jump if the carry flag is set. And so you can do these kinds of things. See, multiplication and division. These are a little bit complicated. So I say here a 32-bit value times a 32-bit value is a 64-bit value. That is, I mean, it could take up to 64 bits. This is where we go off the rails, but this is the way that IA32 generally works. That 64 bits divided by 32 bits is going to generate a 32-bit quotient and a 32-bit remainder. Are these actually good constraints to follow in general? What if I have a 64-bit value and I divide it by 1? Then I have a problem, right? I've lost some bits. I've lost some precision. So generally, the processor will also tell you if you overflow in these situations with division. So not perfect, but it does the trick. So we have a whole bunch of different ways you can multiply. So imul, source, and dest. And let me see what happens. I think it multiplies source and dest into dest. With the caveat, of course, that even though you could generate more than 32 bits in your product, it throws away the bits above bit 31, if you will. So, like it says here, dest becomes source times dest modulo 2 to the w. And the whole point of it saying imul, the I basically means it's signed integer multiplication. There's also mul, and that's unsigned integer multiplication. So here's 3 argument multiplication. So source 1, source 2 into dest. So dest becomes source 1 times source 2 modulo the bit width of the operation. Okay. So in general, all these registers are going to be the same bit width. You could do 32-bit times 32-bit into 32-bit. You could also do 8-bit times 8-bit into 8-bit if you wanted to. Okay, 1 argument multiplication. This one has some implicit arguments. And you'll notice that it multiplies whatever the source is by the value that's already in EAX. So EAX is a hard-coded argument. So, of course, you could say imul EAX, and then it would just multiply EAX by itself. And then the result goes into EDX EAX. So this is the way of actually preserving the entire result. If you wanted to actually do a correct multiply and make sure you preserve all 64 bits, you could do it this way. Infrequently, I've relied on being able to do this. GCC has some built-in functions that you can use for doing this multiplication and division stuff and preserving all of the bits. And they basically translate down into these instructions. They're encoded so that they rely on these instructions to do it properly. Okay, so you have imul, and then you have mul, which again, notice source. So this time it's unsigned multiplication. So whatever the argument is times EAX, and then the result goes into EDX EAX. You have 1 argument division. So again, you take EDX EAX, and when we say EDX colon EAX, what we're really saying is EAX is the low 32 bits of the value, and EDX is the high 32 bits of the value. The combination of concatenating those things together is the value that's being divided, or the result of the multiplication, either way. So EDX EAX divided by source will go into EAX, and EDX gets the remainder. So you have IDivL, and again, I means it's signed, so divL just is unsigned division using the same arguments. Now setting up EDX EAX for division is kind of annoying, but you have a couple of instructions that can help you do this kind of thing. Now since we're generally talking about 32-bit, I'll show you the 32-bit one. And unfortunately it has a different name in the Intel manual, so you have to be aware of that when you want to look it up. But CLTD convert long word to double word. So it'll go from 4 bytes to 8 bytes. And the 8 bytes will be in EDX EAX. Notice that it does sign extension again. So that top bit is going to be replicated all the way through EDX. That way if you're dividing something by, or you're dividing a negative number by something, you can go ahead and compute that. If you need to set up an unsigned value, well, you can just zero out the other register. You could certainly do that. I think there's another instruction kit that can do that for you as well, but I can't remember off the top of my head. Okay? Any questions? All right. Yeah, so varying input widths are also supported, so I kind of mentioned this as we went along. If you want to do two 16-bit values, you can certainly do this. This is what I grew up on because we didn't have 32-bit computers right away. So DXAX becomes source times AX. That's IMOL W. IDiv B, if you really want to be tiny, then IDiv B will take the AX value, divide it by whatever your source 8-bit argument is, and then AL gets the quotient, and AH gets the remainder. So you can do these kinds of things if you really need to. And then, of course, these are the variants of CLTD, or CDQ, I think it was on the other slide. So you have these various options for sign extending values into multiple registers. Okay? So those things are available to use. Few examples. So let's say that X is at location 8 EBP and Y is at 12 EBP, and they're both signed values. So we want to actually do a signed product. Then we have to use IMOL, not just mol. And we can't, we'll use the one argument version so that we can actually get the 64-bit answer. So we move 8 EBP into EAX. That's going to be one of the implicit, or that is the implicit argument for IMOL. And then we multiply it by the value at 12 EBP. And then the answer goes into EDX, EAX. And then we just save that 64-bit value onto the stack. Why, I don't know, but that's what we do. Okay? Certainly you can do this. Sign quotient remainder of X divided by Y. So this time we move X into EAX. We sign extend it into EDX using CLTD. And then we divide it by Y, whatever's at 12 EBP. And then EAX is the quotient and EDX is the remainder. Any questions? If you try to divide by 0, the processor will actually explode. Not really, but it indicates that the computation had an error, obviously. In fact, what is it? It'll generate a fault, a divide by 0 fault, if I remember correctly. I don't know if anybody knows this off the top of your head, but the processor has a few of these kinds of things built in as hardware exceptions, and it'll actually say, your program was dumb. It tried to divide by 0. Okay, flow control. There's a huge number of instructions for doing flow control in IA32. And the simplest one is the unconditional jump, which even by itself is really fancy, and you can do all kinds of nifty things with it. So jump with a label is the obvious one. It's a direct jump. You have jump with star and then a register. So now we can actually use this for jumping to a location that is specified in a register. So jump star %EAX, well, whatever the address is in EAX, that gets loaded into the instruction pointer. Or the instruction pointer. So you want to figure out how to set the instruction pointer to something? Well, load the value into EAX and then jump to it. So that's what you could do. You can also do doubly indirect jump. So the jump %EAX is an indirect jump, but then you have a doubly indirect jump where you can actually put an address into EAX, then the processor will go load the value at that address, and whatever that value was, that goes into the instruction pointer. So this is very, very powerful. You can use these things for implementing all kinds of fancy flow control mechanisms in your fancy programming languages, like continuation passing and all of this kind of fancy stuff. So switch statements are an obvious one. You'll get to explore that. I think that's also on the second assignment. Object-oriented programming will have a table of function pointers for virtual functions. You can use these jump instructions for that. We'll actually explore that in week 4. And there's a few other things that you can do with them as well. I'm not going to talk any more about that because as cool as it is, it's just going to become a time suck. And I'm going to descend into excited but useless discussions. Okay. Everything else. This is unconditional jump. Everything else is a conditional jump in IA32, and it basically looks at the flags register to figure out what to do. And this is where I was telling you before. We had this branching logic where we bring the A register value out into the branch logic. And it was like okay, it wasn't great, but it really limits what we're able to do as far as conditional branching in our programs. Like, what if we wanted to do branch if non-zero? Well, that's fine. We could still do that in the branch logic. But what if we want to do a branch based on if one value is less than another? Okay. Well, now it's starting to get a lot more complicated. We'd have to have quite a few instructions just to implement that. So this is the way that most processors do it. They take the status flags from the ALU, and they'll feed them into the branching logic so that they can actually do things based on the result of some other operation. And in fact, they even are a little bit more sophisticated than this because the status flags go into a register so that they can be referred to multiple instructions away. We don't actually have to just look at them immediately. We can save them and refer to them later. So the ALU generates status flags, and they're fed to the branch logic, and then we can do all kinds of things based on the flags that come out of the ALU. So these are the flags we care about: carry or unsigned overflow, sign flag, overflow flag, which is signed overflow. You have to be careful about that, and zero flag. The result is zero. Okay, so yeah, basically the arithmetic and logical instructions set these flags, and then we can do a conditional jump. Like, what if I want to tell if two registers have the same value in them? Well, I could subtract one from the other, and if the answer is 0, then I could jump. Right? That's one way I could do it. Of course, it's kind of annoying to actually do that modification, and so we have a couple of instructions that do things like that, but they don't save the answer. They just update the status values, and then they use the status values, but they don't actually save the result of the computation. So here we have compare source 2, source 1, which updates the flags as if you had subtracted source 2 from source 1. So it's like you did a subtract and you don't want to save the answer. And then test does a bitwise AND. And again, it doesn't save the answer. So you might have noticed this weird thing. Like, tell me if you noticed this, that we had our processor for the first week, and we had that write bit that we could set in our instructions. Like, every single one of our instructions had a 1 for the write flag, except maybe the branch of 0, because we didn't, that would just look at A. But we had this write flag, and we always set it. Well, this is why we have a write flag, because sometimes we want to do the computation and throw away the answer, but we actually care about the status of the result so that we can use it for doing conditional flow in our programs. Okay, let's see. We have a few examples of these. Yeah, you can't do an indirect conditional jump. They have to have a label or a specific address. So here's a few things you can do. Jump if equal. Now, like I said, if you want to know if two values are equal, you can subtract them, and if the answer is 0, then they're equal. So that's what JE would be. You can also do JZ. That would be jump if 0. And JNE would be the inverse of that. Okay, so jump if sign, jump if not sign. So jump if sign, you're saying the answer was negative. Okay, jump if not sign, the answer was 0 or positive. Okay, JC or JNC, so that's just jump if carry or jump if not carry. And JO or JNO, that's jump if overflow or jump if not overflow. Okay, so you can do these kinds of tests in your code. I very infrequently use jump if overflow or jump if not overflow. Jump if carry is really common. Jump if 0 is really common, and jump if sign is less common, but you do see it from time to time. Okay, now you also have conditional jumps where you can basically say to the processor, so how do these values compare to each other? Jump if greater, jump if less. Now you'll notice that a lot of these have synonyms as well. So jump if greater, if you really like typing, you can also say jump if not less than or equal. That's another option that you can do if you want. And you also have these ones, jump if greater or equal, jump if less or equal. And these basically look at combinations of the sign flag, the 0 flag, and the overflow flag. I might have gotten that wrong. Anyway, let me see if I have that here. Sign flag, over flag, and 0 flag. Yeah, I was right. So I remembered my slide. Yeah, so you have overflow, signed overflow, and basically we're not going to go into all the details of how it figures out these things because it's kind of beyond the scope of what we're interested in. But there certainly is a section in the book that goes into this in great detail. So if you have the book and you're curious, you can look at that section in the book. Okay? Zero flag obviously tells you if they're equal, but then the sign flag and the overflow flag can be used to tell if you're greater than or less than. And so it uses those to implement those parts of the instructions. Okay, now you have signed comparisons, but you can also do unsigned operations, so you have to think about unsigned comparisons as well. And these are slightly different, and they're similar enough to be confusing. So you have jump if above or below is unsigned. Jump if greater or less is signed. So jump if above, and that's unsigned greater than. So you also have the jump if not below or equal if you care. And these are just going to look at the carry flag and the zero flag. Okay? Because remember, the carry flag is going to be set if there is an unsigned overflow. And so you can, again, use that to tell if one value is above the other or one value is below the other. And then you can test that based on that. Zero flag will still tell you if they're equal, so you can use that. Okay? And so in general, when I have you write code, you can usually tell, like, oh, this is a signed value that I'm working with. If it can go negative, you'd better use the sign comparison operations, or else you may find that your code infinite loops, because you subtract, and guess what? For jump if above, it's like really above now. And so you have to be careful about that kind of thing. So that's when you're writing assembly code, you have to think about your arguments. Are they signed or unsigned? Which kind of reminds me, just as a quick side thing I want to talk about before we go on. Sometimes students ask me, well, won't the assembler stop me if I use the values wrong or something like that? And I see some of you smiling, and that's probably a good response. But the question is a very valid question. At this level, you don't really have types. You have a number of bits. And then it's up to you, writing your program, to decide what do those bits mean. Oh, it's a signed value, so I need to make sure I use the signed instructions. It's an unsigned value, so I need to use the unsigned instructions. This is actually 4 bytes of a string, and so these are 4 characters in my string. So I need to treat it that way. Seriously, at this level, it is very, very no holds barred. You can do whatever you want. And if you think about it, that's exactly like when we had logic gates and we built arithmetic out of it. The logic gates didn't care that we were implementing arithmetic. They didn't care, ooh, this is going to be overflow, so I'm going to get especially excited in this situation. The logic gates were just a tool for implementing arithmetic. Assembly language is just a tool at some level for implementing these higher level things. And so we have to make sure that we use the tool properly. So that's I just wanted to mention that as an aside, because sometimes people ask that very valid question, but at this level, there are no types. It's just numbers of bits. Okay, and yeah, there's a lot of other stuff that we could talk about. Various assignments will introduce instructions here and there, but I really do feel like that's the bulk of them. There may be 10 or 20 at absolute tops, maybe just 10 more instructions that you'll encounter in CS24, and I think that you'll probably, you'll have no problem understanding what they do. Now, I do mention the book reading for week 2. It is optional. It's pretty long. There's parts of it that are going to be essential for the assignment, and again, fair use, blah, blah, blah. There will be a PDF, and you can go ahead and look at that stuff. Okay? And yeah, if you run into something and you're just totally bewildered about it, just email me or the TAs or CS24 TAs, and we'll be happy to explain it. There's a lot of nifty things you can do on the Intel processor, but most of the time you'll have a pretty straightforward time understanding it yourself. Okay, so that was all nice, and of course, I said last time. Oh yeah, so this is true. So last time in our last lecture, we did talk about this crazy high-level construct called a subroutine. I have a piece of code and I want to be able to use it multiple times in my program. And the big challenge that we had to sort out was how to get back to where it was called from. And then we had various other peripheral considerations as well, like, oh, I've only got 8 registers, so I need to find out how can I make sure my subroutine doesn't trample on the caller's work and so forth. So we had a lot of details we introduced last time. There are a lot of different options when you're talking about higher level language. We're going to actually take a step up. Now, I say here, this is an example of a scheme environment. Do you guys actually, people who have taken CS4, have you seen these environment diagrams? I sure hope so. I'm really sad that we don't spend too much time talking about these anymore. Not because they illustrate some beautiful, elegant principles of computer science, but you can implement an entire scheme interpreter just implementing the environment model. Like, ooh, I need an environment that has name value bindings, and I can build that in C. I know how to build that in C. And I can have pointers of things, and I can invoke functions, and blah, blah, blah. I can do all that stuff. In fact, in Lab 4, I give you a scheme interpreter that I implemented following the environment model. And it can do some basic stuff, not all kinds of advanced, amazing stuff, because I have other stuff to do with my life. But you follow the environment model, you can actually build some really cool things. Okay? Now, we'll talk about today's code in terms of the environment model, but we won't have lambdas. We won't have these little like double circles that mean crazy things and track frames and so forth. We're going to be sticking with something very straightforward. C functions and some of the abstractions revolving around the C programming language. Because all we're doing is we're taking a little step up the abstraction hierarchy so that we can figure out if I know how to implement C in assembly language, then I can implement other stuff in C, and then I know that I can do all those other things as well. So again, we're obscuring each level of the abstraction hierarchy as we move up the hierarchy. So we won't have any trap frames or lambdas or garbage collection at this point, but we will talk about how to implement garbage collection in the future, because it's a really fun topic. And it is pretty straightforward to implement with IA32 assembly. So these are the things we had to do for subroutines. Figure out how to pass argument and return values. That's a convention. We come up with a convention, and everybody follows it in our program, and we're happy. We have a way to transfer control from the caller to the subroutine in such a way that we can go back. And then we need to be able to isolate the subroutine state from the caller state, which we will also solve with a combination of technology and convention. So here's the program we'll be looking at. It's very, very straightforward. We have an accumulator. So we have this accum function, which will add a value into our accumulator value, which is value up at the top. That's going to hold our running sum. Yes, it's a global variable, and yes, that's a terrible idea, but it's really simple assembly code, so we're going to stick with it for right now. Then we have reset, which returns the old value. Whatever was in value before it will return, and then just zero out value. And then our main function is just really simple. Generate a whole bunch of numbers, a whole bunch, I guess, being 10, 10 numbers from 0 to 999, and print out what the value is, and then stuff it into our accumulator. Okay? That's all our program does. It's really straightforward. So we have a global variable, we have functions, and a main function to exercise the accumulator. That's basically what I just said. Now we have three kinds of variables here. What all kinds of variables do we have? Well, it should be pretty straightforward to figure out. You look at reset and main. They have a certain kind of variable called a local variable because it is local to the function. You can think of the function as having a frame in the environment model, and that frame has a couple of bindings, like main would have I and N. Okay, so that's one kind of variable. We also have value up at the top. That's a global variable. And then we have arguments, and right now we only have N for accum. That's the only place that we have an argument, although you can see that we also call printf, which takes 3 arguments. So these are the 3 kinds of variables. We have global variables, we have function arguments, and local variables. So we have to figure out how we're going to deal with all of these various things when we implement our C program. Now we're not actually going to implement our C program. We're going to ask the compiler, hey compiler, what would you do? And we'll look at what it does, and then we'll get into writing our own programs after that. But it's always nice to look at an expert before we start trying to do it ourselves. So like I say here, the computational model approximately is that we have a global environment at the top level that holds our global variables. If you are already really familiar with C, then you probably understand things like extern variables and module local variables and things like that. So obviously this is not exactly the case, but you can think of it as being this way. Global environment at the top level. When you call a function, you get a new environment whose parent is the global environment. And it holds the arguments and local variables. And what do I say here? Yeah, all functions in the file can access the contents of the global environment when they're invoked. That's just pretty obvious. Okay, so we end up with something like this. So reset has been called. in main. So we're in main right now, so that's the main frame. That sounded kind of corny, but I won't go there. So anyway, I is 0 because we haven't started adding stuff to the accumulator yet. The first n is 807, and what happens is accum 807 is called. Well, accum's parent would be the global environment, so we get a new frame where n is 807, and it goes ahead and adds that to value. And since value is not in the accum functions frame, it goes and looks at the global frame and is like, oh, value's here. And so it just scratches that out and replaces it with 807. Okay? Very straightforward conceptual model as to how C works. It gets way more complicated than this, but we're going to stick to this for now because it's just an easy way of thinking about it. So global variables, how do we represent them? Well, they're global. Everybody needs to be able to access them. So we'll have a simple approach of just assigning an address to it. And anytime we need to access it, we'll just use that address so that we can pull that value out or we can write to it. We'll just do a move or an add that targets that memory address and we can update that global variable. Function arguments, we will store them on the stack. And so like I said here, function arguments are provided by the caller, duh. And so the caller has to put them onto the stack before it invokes the function. And like I say here, on IA32, that'll be a frame pointer plus some offset, or the BP register plus an offset. Local variables will be also on the stack, but they will be below the function argument, so they'll be the frame pointer minus some offset. And the subroutine will be responsible for those variables. Now, I should also give you another caveat, which is that if we can store our local variables in registers, we want to, because using a register is faster than accessing memory. And so generally, we will use registers as much as we can for local variables. Now, we have the stack pointer. I'm not going to spend too much on this stuff because we've already covered these concepts. We have EBP, which is the base pointer, and the instructions call, which pushes the instruction pointer to the next instruction onto the stack, and then changes to adder, changes EIP to adder, and ret, which just pops the top of the stack off. Okay? So this is all exactly like what we talked about before. There's nothing new. I'm not going to spend too much time talking about it. Just remember, ESP always points to the top of the stack. There's always a value where ESP is if the stack actually has anything on it. So ESP always points to the top of the stack. Now, there's a lot of different ways that we can organize these stack frames, and this is what I was saying before. We have to pick a convention and then stick with it. And so calling conventions say how subroutines and their callers are able to interact. And the one that we'll be learning is cdecl, because it is used very widely. I think it's even used on non-IA32 platforms that are running some variant of Unix. So it's very, very popular in the Unix world. And like I said, the caller and the callee have to coordinate because you have these shared resources. You have the stack, where the arguments need to be left, and then you also have the register file. There are processors that allow you to switch to a new register file when you get into a subroutine. Like I said, RISC processors have tons of registers, and so they can do that kind of thing. Oh, we're going to switch to another register file so that the subroutine can do its own thing. But in general, we don't have that facility available to us, so we have to be careful about what we stomp on. Okay, so the calling convention specifies these things. Who sets up which parts of the call, what needs to be saved, who saves it, and how to return values back to the caller, and then who cleans things up. Okay, these are all aspects of the calling convention. So the caller is responsible for setting up arguments, and the way that we do this is that the caller pushes arguments in the order last to first, which is a little bit weird, but it has a couple of benefits. So you see argn being the last thing is pushed first, so it has the highest address. And as the arguments we get toward the front of the function call, they have lower addresses. So the one benefit, which is more of an aesthetic concern, not as important, is that the lower the offset, the earlier the argument. So arg1 will be ESP0 in this case, or something like that. And the higher the number, the further back the argument is. The second one is actually really important implementation detail. What if I have a function that takes 2 arguments and I create 5 arguments for it on the stack? Well, the function only sees the 2 arguments. That's all it cares about. Now you might say, why in the world would I ever have a function that takes fewer arguments than I actually pass to it? Well, if you're writing an operating system, you see many situations like that. In fact, I will show you some if you take CS124. When we do interrupt dispatching, it's really helpful to have functions that completely work fine if they actually say they want fewer arguments than the interrupt dispatch code pushes onto the stack. So we'll table that for CS124, but there are situations where it's really helpful when you're writing an operating system. I think you can also use it when you're implementing system calls as well, but again, we'll talk about that in 124. Okay, yeah, primitive values usually take up a double word, so that's why our addresses decrement by 4 bytes each time. Just be aware of that. And so invoking the procedure, the caller uses call to invoke the procedure, and so the first thing the callee generally will do is set up a frame pointer. Remember, EBP is the register that can be used for the frame pointer. But the caller probably also had a frame pointer, so we need to make sure that we save it. So you end up with something like this. Push EBP, so that decrements SP from the return address, and then move the current stack pointer into the base pointer. So now we have our frame. Okay? So if you look at this, you can now say, all right, for EBP is going to be what? I'm sorry? Wrong. For EBP is going to be the return address. If we actually want to change where we return to, we could do that. Okay? 8 EBP is going to be the first argument, 12 EBP will be the second argument, and so forth. So a lot of times, once you've done this setup, you'll see code that says 8 EBP, 12 EBP, and so forth, accessing the arguments. Now this rule, the callee must save EBP before it changes it. Because remember, we only have 1 EBP on the processor. This is an example of a larger problem, which is that the register file is a shared resource, so we have to figure out who's responsible for saving things. And so we have 2 categories of registers. We have callee save registers and caller save registers. Callee save registers, like it says, when the callee returns, the registers better have the same values that they had when the function was invoked. So if the callee changes these registers, it needs to save them on the stack before it changes them. So these are the registers that are callee saved: EBP, EBX, ESI, EDI. Caller save registers are one where the callee, or the subroutine, is allowed to trample on them to its heart's content. If the caller wants those values to be preserved, it must save them. So the caller, again, so here we have EAX, ECX, and EDX are the caller save registers. Okay? So just be aware of this. Obviously, ESP is the stack pointer, so it needs to be managed properly by the invocation, or else you end up in la-la land. Okay, but this is a very important part of cdecal. Now, the last thing that we're going to talk about is this: how do we return a value to the caller? And we're only going to consider things that are 32 bits in size. And those get passed through EAX. So the callee does its thing, and then says, EAX is my answer, and then it returns to the caller. Obviously, if it needs to restore any callee save stuff, it does. But anyway, the answer is in EAX, and then it restores EBP and then goes back to the caller. Last question. Who removes the arguments from the stack? Should the caller? Should the callee? Well, it turns out that there's different answers, but cdecal says the caller has to clean that stuff up. Okay? That's just what cdecal says has to happen. Okay? But Windows has a different answer. Windows says if I invoke a subroutine, the subroutine has to clean up the stack, which can kind of lead into trouble. Okay? So, like it says here, this is called standard call. And there's another form of the ret instruction where you can actually clean up the stack for the caller right before you return to it. So ret n will pop n bytes off the stack and then return to the caller. Okay? Actually, yeah, so it gets the caller's address and then pops n bytes off the stack. I have to be careful because the arguments are above the address. Okay, any questions? All right, we're going to, let me see. We don't have time for this, so we'll go ahead and talk about that last time. So make sure that you study cdecal. It is extremely important because once you understand it, we can start doing some really powerful and fancy things with it. So we'll go ahead and pick this up next time.